Welcome friends. In the last class, we attempted to understand the definition of state variable, and state model of a system. Let us in today's class try to understand the state space model through an example of DC servo. So let me write the heading: state space model of a DC servo. So in the previous class we studied that if we have a state space model like x dot equals to ax plus br, I'm dropping the independent variable t for ease of presentation, y equals to cx plus dr, where x dot is the time derivative of state vector, x is the state vector, a is the system matrix, b is the transfer matrix, that is the state transfer matrix, c is the output matrix, and d is the direct transfer matrix, direct transfer matrix. So this type of situation is very rare because we don't want to transfer the input or desired input directly to the output. So we are more familiar with the model like x dot equals to ax plus br and y equals to cx. In many books you will see this as, instead of r they have written u. So this term u is little confusing because in control domain we use the symbol u which is entering the plant directly. So this is the plant gt and ut is the input to the plant and yt is the output of the plant. So in case we are using the closed loop control, suppose you are using a controller, then you are using a reference, there is a feedback and it is compared here. So in such cases we don't see u outside, so we can correlate y is here with the input, r is here. So that is why this representation is more genuine and that is less prone to confusion. So sometimes in books you will see that it is written in the form like x dot, they write small x dot equals to capital A small x plus small b small r, then small y equals to small c small x plus small d small r. Here they say that this x is in bold, that is a vector, this x is in bold, that is vector, then this b is in bold, so this is also in vector form, then this c is in bold, this x is in bold, and D and R are simple. So they assume that this is a single input single output system where you have a single plant GT which is having the single controller, and there is single input, so RT, there is single output YT, and again there is a single filter HT. So naturally, to cope up with R, your B should also be small. So this is the this B and this B are different. So let us write this as B1 for the time being. Now you should be careful that here you are taking single input single output system. So whatever be the number of inputs and output of the system, the state variables can be one or more than one. So it has to be the vector. It has to be the vector. So you keep it in bold. So that is why I am showing here it vector. Here also, because x is suppose n by 1 vector, this is n by 1 vector, and r is a constant, so naturally b is also n by 1 vector. So it is represented like this. So be careful, you need not be confused with this. Now here, what is the relation between c and x? C is a transpose of a vector, so y is a single element, so naturally c should be something like c1 c2 and this cn, then multiplied by your x1 x2 up to xn. So then this complete thing is a single value, so that is compatible with y. So that is why this is also vector, x is also vector, but c is basically transpose of a vector. Then because r is a single element, y is a single element, so d is also a single element. So this kind of representation is also possible, so you have to be careful when we are treating with a single input single output system. We are doing like this. Now we will see how we can represent such single input single output systems. Then we will compare it with multi input multi output systems also. So let us represent, I want x from y, sorry, I want x, this is vector x, from r, the reference input, this is a single input. Then I want y from x, so I have something over here, then I have y, this is again single output, and this x dot, this is also vector, is equal to ax vector plus b vector r. So this is the system from where I am getting x, and so this is naturally n state variables and y equal to c transpose of a vector, so you are representing a vector cx plus dr. So this is a kind of representation where, so dr is taking r as input, so we can connect it like here in this way, and this is br. So this is one of the representations possible, but here we have the initial value of x also taken into count, because whenever I am considering a system, I am defining a state, so it can have an initial value. In case of multi-input multi-output system, where instead of this single y we have many y's, y1 y2 up to yp suppose, so the system will have many outputs. So in that case we will consider multi-input multi-output system, MIMO, MIMO. So in that case we have, suppose m inputs. So this is r1 r2 up to rm. So in that case, this MIMO system will be represented as x dot equals to ax plus bu br and y equals to cx plus dr. So, so here you see that all the letters are capital. X I have also taken as capital. You have two options. Either you represent with capital X or you represent with small x with vector, because on pen and paper you cannot show it with bold letter X. So that is why I am using the capital X. While you can also use small letter, but try to use the vector symbol to show that X is a vector. So with this understanding of state space model, let us try to understand how the DC servo can be represented as a state space system model. So as you have learned in your basic control systems class, that this servo system is representable in terms of various parameters of the DC motor. So let me take the advantage of your knowledge on that and do it a little fast. I will draw an armature controlled DC servo which is separately excited. So let me draw the armature controlled DC servo. DC servo separately excited. So what you can do, RA, LA. So these are circuits you already know. This is the series inductance and series resistance of DC motor, armature resistance and armature inductance. Then we have the supply over here. You have the supply over here. So this is coupled to a load which is a mechanical load. So this is J, this is B, then there is angular velocity, that is the constant speed it is rotating for a given voltage. Then you are developing a back EMF, as you know, as the speed grows the back EMF grows and that balances the armature current. And with this we write the circuit equations. So here you have the UT. So I'm starting with the supply voltage. UT equals to armature inductance L d by dt of armature current as a function of time plus armature resistance into Ia. So I am using the Kirchhoff's voltage law. So this is back EMF. So with this this circuit is completed. So then we have the torque generated. So the torque generated should be, so I write the equations gradually. This is equation 1. So the torque generated over here, the motor over here, this motor generated torque is Tm at T equals to J d by dt of omega T plus B omega T. So this is a standard equation, so we need not worry for that. J is the equivalent moment of inertia, Tm is the torque developed, and B is the equivalent viscous friction coefficient. Then omega is the angular velocity or angular frequency of the motor, and all are in respective units. So we know that this motor generated torque is proportional to armature current, so we can represent it through some torque constant Kt multiplied by Ia. This is equation 3. Then the back EMF is always the function of the rotary speed. So back EMF as a function of time equals to Kb into rotary speed. So this is equation 4. Now I need to retain the armature current and the angular velocity as the variables of the system. So let me remove the unwanted variables one by one. So this Tm can be removed from equation 2 and equation 3. I am eliminating Tm. So if I eliminate Tm from equation 2 and equation 3, I will get J d by dt of omega t plus b omega t equals to Kt Iat. This is equation 5. And similarly, from equation 1 and equation 4, I want to remove the back EMF. So if from equation 1 and equation 4, I remove the back EMF, so it should be La d by dt of Iat plus Ra Iat plus back EMF is removed, so it becomes Kb omega t, and that is equal to Ut. So in the standard expression, the forcing function is on the right hand side, so I am trying to take the things on the right hand side. So if I rearrange equation 5 and equation 6, rearranging equation 5 and equation 6, we get so from here I am dividing both sides by La and taking these terms to the right hand side, so then it becomes d by dt of Iat equals to minus Ra by La Iat minus Kb by Ila omega t plus 1 by La Ut. Now this is equation 7, and similarly I am rewriting the equation 5, so it becomes, after dividing by j on the both sides and taking the non-derivative terms to the right hand side, I am able to construct the equation like this. D by dt of omega t equals to Kt by j Iat minus b by j omega t. So this is equation 8. So now you see that on the left hand side we have first order derivatives of the variables, and on the right hand side all the terms are linear, there are no derivatives with respect to the independent variables. So this is the standard format for the state equation. Now I decide the state variables. So once I form the standard form, then I can decide that, okay, let us take x1 at t equals to omega t and x2 at t equals to iat. So now we can write this is as x1 is I am placing here. So x1 dot d by dt of x1 is equal to x1 dot equals to, so when omega is x1, so this I have to take care, it should come first. This is equals to minus b by j of x1 and plus kt by j of x2. Then the other equation we have d by dt of x2 equals to x2 dot equals to, here this term is the x1 part, so I write minus kb by la x1, then minus ra by la x2, and we have plus 1 by la ut. This ut is basically the forcing function, that is the voltage applied to the servo. Voltage applied to the servo. So this we can write in the matrix form because we already got the state space model. So from here we get the matrix form x1 dot and x2 dot equals to minus b by j kt by j minus kb by la minus ra by la. This is x1, this is x2, plus you have first one you have nothing, so it is 0, and second one is 1 by la, so this is ut. This is the situation where I am just designing an open loop plant. This is just the design of armature controlled DC servo open loop. So you have to be careful about it because in the books there are sometimes the explanations and diagrams are not in parity. So this is the part of a closed loop control system, that is DC servo plus load. So this is equivalent to this one, and here the ut is playing the role, that ut is entering the DC servo and you are getting the output as omega here. So now before this you can have the controller, transfer function, then you can have the measurement of the output speed through tachogenerator, then you have comparison of the reference input. So I am giving a reference input voltage ER which is being compared with the tachogenerator output voltage. Many times it is given as generator EG, tachogenerator output voltage as time. This is minus, this is plus. So you see, again we can find that this is the reference input R. Okay, so once we design the complete closed loop system, so there will not we know there will not be any visibility for UT. So UT is visible only when we are treating the DC servo in the open loop. So you have to be careful for this. Most of the times because of the notations in the book, we are getting confused. And in case you need a DC servo rotor output position as the output, so you will be required to place an integrator over here that will integrate the angular velocity and that will produce the position. But in that case, you definitely require to use the position sensor, which will give the information about the position. So you require the position sensor in that case if you are using the position control. So with this information, we are going to introduce the idea of eigenvalue in the state space model. So eigenvalue and eigenvector play a vital role in the state space model, as well as it has future scope in the machine learning concepts. So in the design, we will see in the next class, we will see in detail why eigenvector plays vital role in the machine learning. We will have some basic idea about this, how it is connected to tensors. So but in this class, let us just introduce how eigenvectors are obtained for a system. So you have a system x dot equals to ax plus br and y equals to cx plus dr. For MIMO system. Suppose we have a system which has single input and single output, just like a DC servo example we have considered. So here we will consider x dot t equals to ax t plus b ut, but b is a vector definitely. So I am writing x capital, so I did not show it as vectors. Y is a single output, here it is omega. Then c is the transpose of a vector, so I can write it as a vector, and x is capital. So where we have a equal to a equal to 0 1 0 0 minus 1 1 0 minus 1 10 minus 10, and b equals to 0 0 10 and c equals to 1 0 0. So then to obtain the eigenvalue, we use a basic concept. I will give the detail about it in the coming lecture, but let us consider that we have an identity matrix multiplied by some values which are obtained from a vector lambda, that is lambda equals to lambda 1 lambda 2 lambda 3. So from here I have obtained lambda into identity matrix. So 1 0 0 0 1 0 0 0 1. Then we have this minus the matrix A. So using this we can obtain a special characteristic equation which is determined by lambda I minus A. So what is that? Equal to 0. So lambda once multiplied with identity matrix, so you write lambda 1, lambda 2, lambda 3, and I am multiplying with identity matrix 1 0 0 0 1 0 0 0 1, and subtracting 0 1 0 0 minus 1 1 and 0 minus 1 minus 10. So for this I am taking the determinant and equal to 0. This will give us the characteristic equation. So these two when multiplied will get lambda 1 0 0 0 lambda 1 0 0 0 lambda 2 lambda 3. This is a matrix minus another matrix 0 1 0 0 minus 1 1 0 minus 1 minus 10. Or if you are taking the determinant equal to 0. My advice to the students is that please do it yourself to have the sense of how the mathematical progression is happening. So we have the determinant of lambda 1 first with first, then the second with second minus 1, the third with third is 0, then 0, lambda 2 plus 1, then minus 1, then 0, then 1, then lambda 3 plus 10. Lambda 3 plus 10 equal to 0. Now you see the beauty of expansion. If we go like this, then we can minimize the operations. So we'll go like this, expand in that direction. So in that case we'll have lambda 1 into determinant of lambda 2 plus 1 minus 1 1 lambda 3 plus 10. This is equal to 0. So we have lambda 1. So we just follow the concept of multiplying the along this row with the cofactors. So this will give us lambda 2 plus 1 and lambda 3 plus 10. Then minus 1 power 1 plus 1 will be plus 1. So there are no issues. And here plus minus 1 power first row, second column is 3. So this is minus 1. And then I have this to multiply it. Here it will be minus 1. So this equal to 0. So here we find that in case of the eigenvalues and eigenvectors, this lambda 1, lambda 2, lambda 3 form the roots of the characteristic equation in such a way that we have lambda 1 equals to lambda 2 equals to lambda 3 equals to lambda. So replace the value, is equal to lambda plus 1, lambda plus 10 plus 1 equal to 0. It means we have lambda into lambda square plus 11 lambda plus 10 plus 1 is 11 equal to 0. So if you solve it, you can find out the different values of the lambda, and with those values of the lambda we can find out the eigenvalues of the system. So this concept is used to determine the most prominent roots of the system when the control paths are decoupled. So this is a quiz for you to obtain lambda 1, lambda 2 and lambda 3, and send it after solving to my email id control systems faq@gmail.com, and these three values will form the eigenvalues of the system. So in the next class we will see how we can use the eigenvalues of a system to analyze the system in state space model. So this much is for today. Thank you for your patient listening.